Okay, now we're going to do problem 63 from chapter 13. An asteroid with mass, so I'm going to use A to indicate that's asteroid. So the mass of asteroid is equal to 2 times 10 to the negative 4th and then times the mass of the Earth. So I'm going to use ME, okay? So it's 2 times 10 to the negative 4 times the mass of the Earth, revolves in a circular orbit around the Sun at a distance that's twice Earth's distance from the Sun. So let's say this is the distance from the Earth to the Sun. So that's called our RE. Okay, and I'm going to use a little lowercase r to indicate that's the radius, not the radius of the orbit, not the radius of the object. So RE, and then you have your RA. That is your RA. So your RA is twice the RE. Okay, and you also calculate the period of revolution of the asteroid in years, and what is the ratio of kinetic energy of the asteroid to the kinetic energy of the Earth. Okay, so based on this information, how do we find the period of the revolution? We have the radius, and we know everything about the Earth, so we can actually use, and then the asteroid has everything in terms of the Earth, so we can actually find out what is the revolution of the asteroid in terms of the Earth years. In other words, again, Kepler's law. So you have your T squared is equal to 4 pi squared, and then Gm, and then RQ. Both the asteroid and the Earth are orbiting around the Sun. So the Earth. So this capital M here is the mass of the Sun. Okay. So what we have here is that we can just plug in the numbers, and so your A. Let's see. So we can actually do very simple, because you express the revolution in years. So we can actually just keep the year. So in other words, if we use this is for the asteroid. The period of the asteroid square is equal to 4 pi square G, and then mass of the Sun, and then RAQ. So we're going to use a procedure very similar to one of the problems that we did earlier. And then you have your T Earth square is equal to 4 pi square, and then GM, and then S, and then REQ. So you can see that this is when we apply Kepler's law to the asteroid, and this is when we apply it to the Earth. So we can actually do a ratio. All this canceled because they have the common. They are the same. So you have your TA square over TE square, and that's equal to RA square, and then RE cube. Okay, and your RA is 2 times RE, so you have 2 and then cube. So what we have here is that your TA, after you plug in the numbers, you'll find that it's basically is equal to your TA. That will be 8.94 times 10 to the 7th. That's in seconds, and then divided by, let's see, 1 year has 365 days, and each day has 24 hours, 60 minutes, 60 seconds. So after you divide all that, then you will get 2.8 years. Okay, so this is the revolution or the periods for the asteroid that is located 2 times the distance from the Sun. Okay, so this is that. And then you also find the kinetic energy, the ratio of kinetic energy. So let's set up the equation first. So that's a Ka. You want to find Ka over Ke. So we need to figure out what is expression for the kinetic energy of the asteroid and the Earth. When you have an object that's orbiting around, around that. So, for example, in this case, when you have both the asteroid and the Earth that are orbiting around the Sun, they are like satellites. So, what is the kinetic energy? What is the expression for the kinetic energy? You do not use 1/2 mv squared if they are moving in a circular orbit. Instead, the kinetic energy has this expression. which is related to the gravitational energy. Your K here is negative U over 2. This is the equation for the kinetic energy when you have an object that's orbiting around, making a circular orbit. So in other words, you have the top part, the kinetic energy of the asteroid will be this, and the bottom part you have this. So you can see that basically you're finding the ratio of the gravitational potential energy over this. Okay? So this is this. And then what we can do is that what is the expression for the gravitational potential energy? That will be negative G, mass of the sun, mass of the, let's say, if this is A, then mass of the asteroid, and over the distance. So the distance is your RA. Okay? And then likewise, your UE is equal to negative G, mass of the sun, mass of the earth, and then RE. So then you can see that when you take the ratio, this goes away because they are the same. So what you have here is that you have your mass of the asteroid over the radius of the asteroid, and then you have mass of the earth over the radius of the earth. So we rearrange this, you have MA, you have your MA over ME, and then you have your RE over RA. And we have all this information because NA over ME, that just gives you 2 times 10 to the negative 4th, and then you have your RE over RA, that gives you 1/2. That's 1/2. So what we have here is that the kinetic energy ratio is 1 times 10 to the negative 4th. And this is how you calculate the kinetic energy, the ratio of the kinetic energy. First of all, the kinetic energy has this expression that's 1/2 U, and your U has this expression GMN over the distance. So this is just basically set up the equation, plug in the what you have, and then reorganize it so that you get to the point that it becomes just the ratio of the mass and times the ratio, the inverse of the radius, and that you get 1 times 10 to the negative 4th. Okay. All right. So let's see, 85. Okay, so let's see what 85 is about. A projectile is fired vertically from Earth's surface with an initial speed of 10 km per hour. So I say initial velocity is 10 km per second. Sorry. Neglecting air drag. How far above the the surface of the Earth will it go? So in other words, this is the Earth. On the surface of the object, on the surface of the Earth, there's an projectile, and it's being fired vertically. Okay, so with the initial velocity, so how far will it go? So you're asked to find how far will it go, and from the surface of the Earth. Okay, so in other words, this is like on the surface of the object, you shoot up something, and that something has an initial velocity, and it will not go all the way to outer space. In fact, because of gravitational pull, it's going to reach up the high, certain point, which we call the highest point, and then it's going to come back down. So your task is to find how far above the surface of the Earth will it go. So again, we need to, and we're asked to ignore the effect of air drag. So we need to consider how many different kinds of energy are present on the surface of the Earth. we know that it has initial velocity, so there is a kinetic energy, and that kinetic energy, because velocity is given, just 1/2 mv squared. In addition to that, there's gravitational potential energy as well, which is just gmn over r, and that r here was just the radius of the Earth. Okay, and so in other words, initial energy and the final energy at this point and at this point should be the same. So this is your EI, this is your EF. We just need to figure out how many turns in the EI and how many turns in the EF. And when the final velocity at this point should be 0, because when it reaches the highest point, which means that it loses all its kinetic energy. And so based on this, you can set up equations. So initially you have 1/2 mvi squared, and then minus, because your potential energy is negative, so it's negative g, mass of the Earth, mass of the object, over the distance. So the separation here is RE. Okay? So this is the energy content of the projectile. After it's been go to certain point, then this is your R. That's just called that R, an unknown, from the center of the Earth to where it is. And then after we find out our R, then subtract the one radius of the Earth from this. That gives us this distance, which you're asked to find. Okay? So this becomes negative G M, and then over your R. Okay? So you can see that the mass is not given, but it doesn't really matter because we can actually factor that out. So what you have here is you have kilometers. So this is times 10 to the 3rd meter per second squared. So you have 1/2, and your VI is 1 times 10 to the 4th. You square it, minus G, the mass of the Earth. And the mass of the Earth, again, that's from the back of the book. The mass of the Earth is equal to, do I have mass of the Earth? Okay, 5.98 times 10 to the 24th. So you have that, 5.98 times 10 to the 24th, and over your R, which is unknown. So, I'm sorry, we're doing this part. And RE, so what is RE? And your RE here is equal to 6.37 times 10 to the 6 meters. So you have 6.37 times 10 to the 6. So that's on the left-hand side. On the right-hand side, that's equal to negative 6.67 times 10 to the negative 11 times the mass of the Earth, and then over this unknown R. So after you plug in to your calculator, you'll find that your R value is equal to 3.16 times 10 to the 7th meters. Okay, so this is your R. And your R here is measuring from the center of the Earth to this point. So you need to subtract the radius of the Earth to figure out what is the distance from the surface of the Earth. So the final answer is R minus RE, and the RE is this. So after you do that calculation, you will get 2.5 times 10 to the 7th meters above the surface of the Earth. Okay. So this is how you would do this problem. So this is basically everything is energy is conserved. So you just consider at this point what kind of energy are present. At that point, what kind of energy are present. Right here, you have both potential kinetic, and when it reaches the highest point, it loses all its kinetic. So everything is in terms of potential. Okay. So that's that. The last one we're going to do is 92. 150 kilogram rocket moving radially outward from Earth has a speed of 3.7 kilometers per second. So V is 3.7 kilometers per second when its engine shuts off 200 kilometers above the Earth's surface. So this is the Earth, and you have the rocket, and the rocket has a mass that's 150 kilogram, and is being moving radially outward from the Earth. Has a speed of 3.7 kilometers per hour per second when it is 200 kilometers above the Earth's surface. So in other words, when it reaches this point, let's say 200 kilometers above the Earth, surface of the Earth, it has the velocity. So we call that initial velocity. That's 3.7 kilometers per second. Okay. And assume that negligible air drag. Find the rocket's kinetic energy when rocket is 1,000 kilometers above the Earth's surface. So let's say now the rocket keeps going until it reaches a final position. Okay, and that distance is 1,000 kilometers above the surface of the Earth. And what maximum height above the surface is reached by the rocket. Okay, so in other words, when the rocket reaches 200 kilometers above the surface of the Earth, the engine shuts off, and it has at that time the velocity is 3.7 kilometers per hour. What does that mean when the engine shuts off? It means that it starts providing the energy to accelerate, which means that it's going to move, it's going to cruise with that velocity. And once so that velocity will not change because there's no external force to change it. So it's going to move. It's going to. So this is it's not going to change its velocity. It's not going to increase its velocity. I should say that. So it's not going to increase the velocity. So you can consider this as initial velocity. And anything past beyond that, the velocity is going to decrease because there's no external force to increase the velocity. Instead, it's going to lower its velocity because of gravitational acceleration. Okay, that's acting to slow it down. So when you reach 1,000 kilometers above the surface of the Earth, what is that velocity that we are asked to find? So again, this is your initial. This is your final, okay? So it is about energy. Energy is conserved. So at this point, what are the energy that we should consider? It is moving with the velocity, so we know that there's kinetic energy and there's a gravitational potential energy. Likewise, when they reach at this point, you ask to find what is the final velocity. That just assume that it's not zero yet. So we can find that, and we can also find out what is the gravitational potential energy at that point as well. So you have your Ki plus Ui is equal to Kf plus Uf. Now, because this is a linear motion, this is not the object that's making the circular motion, so we cannot use Ki that's equal to negative 1/2 Ui. That will be incorrect. Instead, you would just use the traditional 1/2 mv squared. Okay. So what we have here is this. So let's see. So this is basically 3.7 times 10 to the third meter per second. Okay. And so your Ki, you'll have 1/2, 150, and then 3.7 times 10 to the 3, you square it, minus your G. So your capital minus G. So let me just rewrite it here. I like to have the equations first. So you have 1/2 mvi squared minus G and me over your ri. And that's equal to 1/2 mvf squared minus gm me over rf. That's the equation we go by, so that's plug in the number. So you have 6.67 times 10 to the negative 11, the mass again, and the mass of the Earth. That's your me. Your me is equal to 5.98 times 10 to the 24th. So you have this, and then times 5.98 times 10 to the 24th over Ri. What is Ri? It is 200 kilometers above the surface, so you have to include this. So your Ri, this is your Ri. Okay, so your Ri is 2,000 times 10 to the third, and then plus the radius of the Earth. The radius of the Earth is equal to 6.7 times 10 to the 6. So your RI is equal to 6.57 times 10 to the 6 meters. So that's your RI. So you have this. And that's equal to 1/2 the mass of the object, and then Vf squared minus G, 150 mass of the Earth over the distance. What is that distance? So that distance now is this, from the center to O here. So your RF is 1,000 times 10 to the third, and then plus the radius of the Earth. So you should get your RF, that's 7.37 times 10 to the 6 meters. So it's 7.37 times 10 to the 6. So you can see that. You can calculate this, you can calculate this, you can calculate this, and then you can solve for this. So your VF, after you do the calculation, your VF is, wait, what is it we'll ask to find? Let me see. You're asked to find, kinetic energy. If you're asked to find kinetic energy, then of course you can just leave this as, so that will be just your KF. Okay, so that's even easier. So your KF, after you do the calculation, that will give you 3.8 times 10 to the 7 joules. And of course you can calculate the velocity, because that would just that would just be equal to 1/2 mvf squared. So you can calculate your VF, and I did not calculate. So let's leave it at that. So that's part A. And for part B, what maximum height above the Earth, above the surface of the Earth is reached by the rocket? So in other words, now the rocket will go further until it reaches that point that it loses all its velocity, which means that the final kinetic energy is 0 at this point. So you also find what is that distance. So you can see that, again, we still use this equation, but now our final point is not 1,000 kilometers above. Our final point is right here, and we don't know our R. So we can, so our R here is a variable here. Okay, so what we have here is that you can plug in, so we can still use this equation. So you have 1/2 mass, and then initial velocity squared. All this stays the same, but then on this side, there's no more kinetic energy, because the final stage, this is where we reach the highest point. So no kinetic energy, and then minus this, and your R is this. We don't know our R, F. Okay, so you still use that equation. On the left-hand side equation, that's your starting energy, so it will not change. On the right-hand side equation, the rocket loses all its kinetic energy, so everything has to be in terms of potential energy. So after you do the calculations, your RF is equal to 7.4 times 10 to the 6 meters, okay? And then your R, so this is so the RF is from the center of the Earth all the way to that point. So you need to subtract the radius of the Earth to get the right answer. So above the Earth's surface, that will be your RF minus the radius of the Earth. So when you do 7.4 times 10 to the 6 minus the radius of the Earth, which is 6.37 times 10 to the 6, you will get 1.03 times 10 to the 6 meters above the Earth, and which is about 1030 kilometer above. It's about 1,030 kilometers above the surface of the Earth that the rocket is going to it's going to lose its velocity and reach the highest point. Okay.